Hello and welcome to Lecture 16 for the graduate course ECE 254B, Parallel Processing. This is the last lecture for the course and it covers selected topics from part 5 of the textbook, in particular chapter 17 on emulation and scheduling, and a little bit from chapter 18 on data storage and I/O. Part of chapter 18 we have already covered, so basically the remaining material will be what I'll cover in this lecture. So let's get started. Chapter 17 is entitled Emulation and Scheduling. Scheduling is essentially self-describing. Emulation is a little bit perhaps less obvious, and I'll define what we mean by emulation. So here basically I show in this slide that both scheduling and emulation are instances of mapping of graphs onto graphs. So in scheduling, we have a task graph shown on the left and an architecture 1 in the middle, and we want to map the task graph onto the architecture. In other words, assign tasks to various processors in such a way that the tasks can be executed and their communication requirements, shown as arrows or prerequisite requirements, can be honored efficiently. So for example, if you look at the task graph, this yellow task at the top is a prerequisite for these two white nodes. Of course, here I've not shown any characteristics of the task, the running times and various other parameters. It's just showing the dependencies, data dependencies. So the yellow task basically supplies information to these two tasks, and therefore it's a prerequisite. It has to be executed before these two are executed. Okay, and when the yellow task at the top is completed, it has to send data to these two other tasks. The amount of data we don't know from this task graph. It can be just one word, just one numerical result, for example. It can be tons of data. If it's a lot of data, then it does matter how we map the graph here in terms of communication requirements. So if this yellow node is mapped, let's say, to this corner node, and then the two white nodes are mapped to these two nodes, then the yellow node can communicate with these two directly, and therefore these two data transfers can be done rather efficiently with that particular mapping. So even if there's a large amount of data transferred between the yellow task and the two white tasks, it can be done quite efficiently. On the other hand, if the yellow task is mapped here and the two white tasks are mapped, say, over here, the opposite corner, then the data transmission between them will not be as fast or as efficient. So basically, it's a very difficult problem. This is the best mapping of this task graph. Other things must also be considered. You notice that this task graph has more tasks or more nodes than the architecture. Therefore, some of these nodes will get assigned more than one task to execute. You remember from our previous discussion, this we call load factor. So the load factor will be greater than 1. And depending on how you distribute these tasks among the nodes, what the running times of the tasks are and what their dependencies are, the efficiency or speed of execution will be affected. Uh, most scheduling problems, as we will see later, are NP hard. In other words, if you have a large task graph and a large architecture, there is no efficient algorithm for doing the mapping optimally. So we'll talk about this in greater detail. So in the scheduling problem, we assign tasks to compute nodes so as to optimize system performance. The goal of scheduling is to make best use of nodes and links. Once derived, schedules may be adjusted via load balancing. So we make an initial decision about what tasks are mapped onto nodes, but because the running times of tasks, even if given to us, they're usually estimates. The running time will differ from one execution to another because it may be data dependent. So if midway through the execution of tasks, we notice that some nodes are overloaded, they have more work to do, others are idling because either their tasks were completed rather quickly or they're assigned tasks that cannot execute yet because the prerequisite tasks have not been completed, then we may do load balancing, basically transfer some load from one node to another node in order to rebalance the system. Now, load balancing has some overhead. Transferring of tasks requires overhead. So one has to be judicious in how much and whether or not transfer things around because uh, that load balancing pays off only if the gain in execution speed is greater than the overhead that you paid for load balancing. Okay, so that's the scheduling problem. Emulation is basically mapping one architecture onto another architecture. It's a problem of the same nature as scheduling. Again, you're mapping nodes of this architecture 1 to nodes of architecture 2 and links of architecture 1 to links or paths in architecture 2. Here too, nodes will be mapped to nodes, and these links or data transfer paths can be mapped onto links or onto paths. Okay, if the nodes are not adjacent, they can be mapped on. The same applies here. And the idea is that once you have done this mapping, any algorithm for architecture 1 can be executed on this architecture 2 by architecture 2 emulating architecture, essentially doing the job of architecture 1. So whenever a particular node here was executing something, if that node is mapped, let's say, to this node, then this node will do that computation. Okay? Whenever some transfer occurs from this node to this node, say, then depending on where that link has been mapped, as I said, it can be mapped to a link or it can be mapped to a path, then data transfer over that link or path will occur. Again, the idea is to make this emulation as efficient as possible. So we try basically, whenever possible, to map adjacent nodes in this architecture 1, sometimes called the guest architecture, to adjacent node into this architecture 2, which is sometimes called the host. So this architecture is hosting this guest architecture. Okay, so why are emulations useful? We can develop algorithms or schedules quickly for a new architecture. So if this is a new architecture, and this is an old architecture for which we have already developed an algorithm, or we have done a scheduling, completed a scheduling task, then emulation basically transfers that algorithm to this architecture, or that schedule is transferred to this architecture. We don't need to do things from scratch because that emulation basically defines how the work of this architecture is done by this architecture. Okay, so it's a one-time thing. You do the mapping, and then that mapping can be used in different contexts with different algorithms, for different schedules, and so on. You don't need to repeat everything from scratch. Another aspect of this emulation is that you can program or schedule on a user-friendly architecture. So let's say mesh is more user-friendly than, say, this butterfly architecture. It's easier for us to develop algorithms for mesh or torus. This is a torus, actually. Then we can develop our algorithm for that and then emulate it on this. Remember, I mentioned that the shared memory architecture is user-friendly in the sense that the programming model is very similar to what we are used to in doing sequential programming. So we can develop, for example, an algorithm for shared memory and then emulate shared memory on whatever architecture we are trying to use. And therefore, the shared memory algorithm can be executed on this architecture. And if the mapping is efficient, then the execution will be efficient. Another application of embedding or emulation is to show versatility of a new architecture by emulating the hypercube on it. Okay, we have shown in the previous chapters that the hypercube architecture is pretty user-friendly for developing algorithms, and also is pretty efficient in executing a wide class of algorithms. So if a particular architecture, let's say butterfly, can emulate the hypercube efficiently, that's an indication that this architecture is also efficient and versatile. Because hypercube is versatile, and this one can emulate the hypercube efficiently, and therefore that's a sign that this architecture is also versatile and useful. Okay. Now, both of these graph mapping problems can also be approached by a problem called virtual network embedding. So this is a higher level view of those kinds of mappings or embeddings. So what is virtual network embedding? This is an area that has been very active in terms of research over the past couple of decades, the last decade in particular. So this is a problem of interest to, let's say, internet service providers and other communication network providers. So there's a substrate network or a physical network that the offerer of service has, and this substrate network, so substrate is also basically equivalent to physical. It has nodes with various capacities. View these capacities, the numbers next to nodes, as the computational power, how much computation the node is capable of doing. A larger number means this is a more powerful node computationally than this one. And then there are links between these. Also, links are labeled with numbers, and that's an indication of capacity, communication capacity, or bandwidth of those connections. Again, different connections have different bandwidths or different capacities. So this is the set of physical resources that we have, a bunch of nodes and a bunch of links with given capacities connecting them. Then different users have requests for virtual networks. So you can imagine that this is, let's say, AT&T that owns a physical network. And these may be smaller ISPs or network providers that want to buy service from AT&T. So this is a particular provider that wants 2 nodes and this much communication capacity between them. Okay, so this is basically a user. A user can be an individual user or a group of users represented by a particular network provider. So these examples are small so that they can fit on a slide. Typically, the substrate network is huge, and each of these virtual network requests can also be large. Okay, virtual network request 2 requires 3 nodes. So these are nodes A and B with capacity 11 between them. This is C, D, and E. C, for some reason, is written sideways. With these capacities required, 7, 7, 10, and these communication bandwidths between them. And virtual network requires 3, also has 2 nodes F and G. With these computational capacities and this communication capacity between them. Okay, so this is a simple abstraction of the problem because the nodes can be characterized by more than one parameter: computational power, storage capabilities, and so on. It can be more than one, but in this simple abstraction, we just take one number. Now, we want to map these virtual networks onto the substrate or physical network. So for example, let's say A and B, little a and little b, are mapped onto big A and big B nodes. This is one particular mapping. It doesn't have to be done in this way. Once we do this, A uses up 12 units of this computational capacity, and B uses 12 units of this one, so there's plenty. There's a leftover in each case. And the communication capacity 11 is provided by this link, which has a capacity of 17. So there's leftover here as well. Okay. Similarly, excuse C, D, and E are mapped here. Again, C requires 7 units of computation. D requires 7 units. It's mapped here. E requires 10 units. It's mapped here. Okay. C to D requires 8 units of bandwidth. D to E requires 8 units of bandwidth. And E to D requires also 8 units. It has to go through 2 steps, but both of these links have enough bandwidth to support that communication. And finally, F and G are mapped here. Between F and G, we need 12 units. So we basically redraw this graph as 2 channels with 6 units of bandwidth, so that we can map one of those channels onto this path and the other channel onto this path. So you can imagine, if with the substrate network of size 7 nodes, and virtual networks of size 2, 3, and 2, there are a whole bunch of options where to map the nodes and how to map the links. And finding the optimal mapping actually is a very difficult task. Imagine if these networks have thousands of nodes, then it's basically hopeless. So there are a lot of heuristics for solving this virtual network embedding problem in a manner that is close to optimal. Okay, we can't find the optimal in a reasonable amount of time, so suboptimal solutions using heuristics. Virtually every month you see papers appearing in various journals dealing with this kind of communication in parallel processing problems, dealing with virtual network embedding. So basically, you see that this is a more general formulation of both the scheduling and the emulation problem. So in scheduling, these virtual networks are basically task graphs. Okay. In emulation, these virtual networks are guest architectures, and this is the host architecture. And basically, we are mapping not just one guest architecture onto this host architecture, but simultaneously we are interested in mapping multiple guest architectures onto a host. Okay, so if we have a good solution to the virtual network embedding problem, perhaps by choosing and adjusting its parameters, maybe we can use the same strategy, same solution approach to solve both the scheduling problem in a suboptimal but close to optimal fashion, and emulation similarly in suboptimal but close to optimal fashion. Okay, so this is basically all I wanted to say in general terms about scheduling and emulation. There are a bunch of emulation results that I go through rather quickly without going through the details because there are a lot of material that I want to cover today. I don't have time to provide lots of details for all of them, but the details are in the slides, and you can study them on your own if you are interested. First of all, remember when we mapped an architecture onto another architecture, we talked about three parameters, which we call load factor, congestion, and dilation. Okay, load factor was how many nodes, in the worst case, are mapped onto one node. So basically, here we have 16 nodes in the guest, and we have 32 nodes, 8 times 4. So there are more nodes than we need, so we can, if we want, we can have a load factor that is equal to 1. Okay? However, in general, load factor can be greater than 1, and that's one source of slowdown in emulation. The other one is dilation. That's when a particular link is mapped not to a single link, but to a path, let's say, of length 3. So maybe this link, because of our mapping, is mapped to this path of length 3. So we say that dilation, the largest of those determines the dilation. Let's say dilation is 3. And then finally, congestion is when multiple links are mapped. So here, for example, a node has degree 4. Okay? In the butterfly network, also each node has degree 4. So it's conceivable that we can avoid congestion because if I map this node, let's say here, and then the 4 neighbors of that node to the 4 neighbors of this node, which are this one, this one, this one, and this one, then I can avoid congestion. But that may not be possible depending on the basically topology of the network. That kind of mapping may not be possible. So in general, we may end up mapping more than one link onto the link here, and that's the congestion. So if in the worst case, maybe 3 links are mapped onto one link, then congestion is 3. So the first general emulation result says that a slowdown in emulation of this architecture by this architecture is upper bounded by the product of dilation, congestion, and load factor. This is obvious. Load factor, of course, because each node does more work, leads to slowdown. Congestion leads to slowdown, because if 3 messages have to go over a link, conceivably it takes 3 times as much time. And dilation also leads to slowdown. Of course, this is a worst case scenario. By proper use of the links and nodes, we can avoid this much. So if this is sort of a worst case condition, it shows that actually this bound can be reached, even though it's a pessimistic upper bound. It can be reached in some cases. So if I map a complete graph, complete p-node graph into this 2-node graph, then P over 2 nodes will be mapped here. P over 2 nodes will be mapped here. Load factor is P over 2. Dilation is 1 because, all the nodes that are directly connected to each other in the complete graph either reside in the same node here or are directly connected. So dilation is 1. And congestion is P squared over 4. In other words, the P over 2 node and P over 2 nodes here in the complete graph are connected. Each one of these is connected to each one of these. So there are P squared over 4 links that are mapped into this single link. And that basically dictates the slowdown. Of course, it's possible to, if the, let's say, communication can be overlapped with computation, as this one is doing the computation for one node, maybe we can do the communication for another node so that we overlap, then maybe slowdown will not be a product of these two numbers, but somewhat less. Okay, the second general emulation result, which is pretty easy to prove, is that the exclusive read, exclusive write PRAM can emulate any degree D network with slowdown factor order D. So if D is a constant, for example, we are dealing with a mesh, that means the slowdown factor will be constant. So in that sense, the PRAM, even this lowest power model of PRAM, is a pretty strong model in the sense that it can emulate any degree D network if D is a constant but constant slowdown. Okay, so here's how that is proven. I'll just show you the diagrams without going through the details of the proof. If you have a degree D network, you can convert it into a bipartite graph by making 2 copies of each node. So node 0, node 1, node 2, node 3. These are the U copies of those nodes. These are the V copies. And if there's any connection from 0 to 1, then there will be a connection from 0 to 1. If there's a connection from 1 to 0, there will be a connection from 1 to 0. So this bipartite graph basically shows the connectivity. And then because the node degree is 3 for these 2 nodes and 2 for those 2 nodes, I add these dashed lines to make the node degree uniformly equal to 3. Okay, so I form a bipartite graph of node degree uniformly equal to the maximum node degree in this graph. Then the rest is simple. Any bipartite graph like this, you can find what is known as a perfect matching. The perfect matching is basically a subset of links that includes all the nodes. Okay? So when you find a perfect matching consisting of these red links, okay, that's basically a subset of the links here that cover all the 4 nodes on both sides. That perfect matching can be emulated by the PRAM in one step. Okay, you can imagine that these are memory locations on the right, and these are processors. And because a perfect matching is basically a one-to-one or permutation connection, then the PRAM can emulate it in one step. Then if you remove those red links, okay, then the rest of the graph will be of degree 1 less because you have removed 1 link from each node. So this was degree 3, this will be degree 2. Again, you find a perfect matching in this graph. In this case, the blue dashed lines constitute the perfect matching. And that's one more step of the PRAM. And once you remove that, you're left with a third perfect matching. So the node degree was 3, and the PRAM can emulate it in 3 steps. Now, what I didn't tell you is how to find those perfect matching, but those are known. The algorithms exist for perfect match. Okay, now section 17.2, I'm going to skip distributed shared memory. And it contains various slides about how to so this is basically the reverse problem. I showed that PRAM can emulate any constant degree network. Here I'm trying to show that the constant degree network, namely butterfly, can emulate PRAM, or shared memory, rather efficiently. Even though it is much less capable than PRAM, it has far fewer connections. By proper scheduling of activities, by proper emulation, which is pretty difficult. That's why I'm skipping this. You can emulate PRAM with only log 2 logarithmic slowdown. You remember, PRAM represents complete connectivity, or degree P connectivity. Butterfly is degree 4 connectivity. Each node is connected to 4 nodes. Okay, so it's rather surprising that this butterfly network can emulate that very richly connected complete network of PRAM with only logarithmic slowdown, but that can be done, and this is basically the subject of this section that I'm mostly skipping. Okay, now we come to the task scheduling problem, which I will cover in some detail because it's one of the more important remaining topic in discussing parallel processing. Okay, as I mentioned, task scheduling problem consists of, given a task graph, to map it onto a set of processors with various processing and communication capabilities. So in the simplest case, all processors have the same computational capabilities. So we are simplifying the problem in order to be able to discuss it within less than an hour. Scheduling can be the subject of one or even two courses in itself. There's so many different algorithms, so many considerations. So we are really vastly simplifying the problem by assuming that all processors have the same capabilities. For the most part, we assume all the tasks also have the same running time, unit time tasks, another simplification. Okay, but in general scheduling problems, the running time for tasks are given. And even if you have different running times, that's still an abstraction or simplification, because the running time of a task is really not known ahead of time. It depends on what kinds of computations it encounters dynamically as it executes, what kind of data is given to it, what kind of interactions arise in the course of computation, input outputs, interrupts coming in. So there are so many factors that we are ignoring by assuming that the running time of tasks is known a priori. And it's even a greater simplification to assume that the running time is just one, as we assume here. The creation of tasks can be static or dynamic. Static means that the static configuration of tasks is given to you ahead of time and doesn't change. Dynamic means that the task configuration changes. So for example, when you execute task 3, it may decide to spawn or create 3 subtasks, or it may decide to create 2 subtasks or 4 subtasks. So these change over time, okay, or in different executions. So for the most part, we assume the static task scheduling problem. Tasks may have importance or priority. We do want to execute all of these tasks. Some of these may be more important than others. So if these tasks are, for example, various tasks that are executed on a spacecraft, let's say. Okay, some of these tasks that have to do with guidance and control of the spacecraft may be more important than other tasks that deal with imaging or other less critical tasks. So tasks may have importance or priority. So if we have limited resources, we may execute higher priority tasks. Or if the task system is periodic, so that we execute these tasks once every 30 minutes, let's say. Okay? Again, if the resources are limited, all the critical tasks may actually be executed once every 30 minutes. The less critical tasks may be sort of sent to the background and executed less often. So there are a lot of layers of complexity that we are ignoring. Relationships we are considering precedence. So 1 precedes 2. I can't execute 2 before 1 has completed. Even here, I did mention in a previous lecture that this dependence may not be basically something that this task has to wait for this one to complete before it executes. The dependence may be in terms of message passing. So somewhere in the course of its execution, this task sends a message to this task. And once that message is sent, this one has what it needs and it can execute. And this message can be transmitted before task 1 is actually run to completion. So again, just saying that task 1 must be completed before task 2 is executed is a simplification. Tasks may not all be available at time 0. So for example, this task is released or becomes available for execution at a particular time. So that's known as the start time. So even if I execute 1 and 2, if the release time of task 3 has not yet arrived, then task 3 is not available for execution. And taking those start times into account complicates scheduling decisions. And finally, tasks may have end times or deadlines. So, for example, this task 10, of course, it's a prerequisite for task 13, but may itself have a deadline. It must be completed by a certain absolute time for it to be useful, okay? So if the deadline is missed, either the task is rendered totally useless, or sometimes we have something called soft deadlines. A soft deadline is not 0 or 1. Basically, you try to make the deadline, meet the deadline, but if you don't, then there's some penalty associated with missing the deadline. The task does not become completely useless, but less useful, let's say, if it's completed after the specified deadline. These are known as soft deadlines, okay? As opposed to hard deadlines, where hard deadline is when the task is rendered useless if it misses the deadline. So you see that there are a lot of factors that we will be ignoring in our simplified discussion. Also, scheduling can be preemptive or non-preemptive. Preemptive, you can view one of these tasks, for example, as reading a book. You're reading a book, and then suddenly the phone rings to interrupt reading your book. Maybe you bookmark it, answer the phone, a higher priority task, and then go back to reading your book. That's a preemptive scheduling. You can basically abandon a task midway through its execution and then return to it. Okay? This kind of preemption often is associated with an overhead. Okay, now bookmarking and going back to that page has very little overhead. Sometimes you may restart your reading, a paragraph before where you bookmark to sort of remember where you were and what the context was. So that's the overhead. In the case of task scheduling, the overhead may be more because once you set aside a task, you have to save the state of the task. save the data associated with the task so that when you return, you can sort of resume execution from that point with the state of the task at that point and with data the way they were at that point in the task. So preemption often is associated with overhead. Of course, sometimes you have no other option if you have tasks with very high priority and you're executing this task, waiting until this one completes before taking on the higher priority task may not be an option. You may have to sort of accept that overhead and do preemptive. The type of scheduling that we consider is non-preemptive. Basically, in the case of unit time tasks, that's pretty, you assign time in units, and once a unit of time is assigned to this, then you might as well let it finish before executing anything else. And then scheduling can be done at fine grain, medium grain, or coarse grain. At fine grain, this task graph, each of these tasks may be a very small amount of computation. In the extreme, each of these can be an instruction. So these can be instructions being executed and their dependencies, data dependencies. And the processor that is capable of multiple instruction issue basically tries to decide which of these instructions and in what order to execute. It says, okay, this instruction must be executed first, then this one, then this one. Once this one is executed, these three instructions are independent of each other and can be executed in parallel if we have hardware resources. Okay. Now, when you do scheduling at that fine level, then scheduling decisions must be very simple. The scheduling algorithm must be very simple so that you can implement it in hardware, because you don't have the luxury of executing, a sophisticated scheduling algorithm to decide what to do. These are basically, very tiny computations, and the overhead of a software scheduler is not acceptable. So in hardware schedulers, we basically settle for a correct schedule, even if it's highly non-optimal, okay? Whereas if these are coarse grain, if each of these is a large program, perhaps with thousands or tens of thousands of lines of code, then you can afford to spend time in running a sophisticated scheduling algorithm to decide in what order and on what processor to execute each of these tasks. Okay, so this basically introduced us to the nomenclature or terminology for scheduling algorithms. As I said, in most of these cases, we take the simplest option among the available options. Now, the scheduling problem is much older than computers. Way before computers came onto the scene, people did what is known as job shop scheduling. So let me explain what job shop scheduling is. So a job shop, of course, this is a modern job shop, but even 200 years ago, something similar to this existed, where there is sort of a workshop with different machines. These were basically mechanical machines like a drill, a lathe, a pipe bending machine, or all the things that you can deal with mechanical items, mechanical pieces, shaping and forming mechanical parts. Okay, so the job shop has a manager who basically assigns tasks to be executed to people who work in the job shop and to machines. Okay, so here's an example. Suppose we have 4 jobs, A, B, C, and D, and each job can have multiple tasks. And those tasks must be executed in order. So job A has task A1 and task A2, and you have to execute this one before this one. B has 3 tasks, C has just 1 task, and D has 2. Okay? Each task, which is part of a job, requires the use of one of the machines in this job shop. And in this example, I've assumed you have just 3 machines. M1 blue, M2 green, and M3 orange. Okay? And then it requires a certain amount of time, 2 units of time, whatever the unit is. Maybe time is assigned in increments of 15 minutes or 10 minutes, whatever. 2 units of time, and 3 people have to work on that. So these are the resources that are devoted to that particular task. A machine, over a certain time period, and 3 people need to work on accomplishing that task on machine M1. Okay, so similarly, each task has, okay, so task A1 can be characterized as a 2x3 rectangle. Okay, so this is task A1. It needs 2 units of time and 3 staff members. So the job shop manager can basically cut tiles in these sizes, a 2x3 tile that is blue because machine M1 is blue, a 6x2 tile that is orange, okay, here's a 6x2, 6 time units, 2 staff members. And then the manager should put these pieces next to each other like a puzzle in order to achieve some goal. So the goal is basically finish all these tasks in the shortest amount of time. Okay? But of course, the time itself is not the only important criterion. How many people you're using, in this case 8, is also important, because if you use 8 people versus 6 people in the second schedule, okay, the salaries of those 8 people will be more than of course, if this job shop is already employing 8 people, then this may not be an important. But if these are, say, hourly employees that can be sent home, if there isn't enough work for them, then of course you prefer to use 6. But in these 2 schedules, you see that this one takes 13 time units to complete. This one takes 16 time units. Okay, so there's a trade-off here. More people, shorter time. Fewer people, longer time. And then you may decide that the product of these two, 6 times 16, which is 96, versus 8 times 13, which is 104, is your criterion. Now, putting these tiles next to each other, you also have to make sure that constraints are satisfied. What are the constraints? If you have one machine M1, one machine M2, one machine M3, you can't stack blue tiles or orange tiles or green tiles on top of one another, because at any given time, there's only one blue machine. In this case, it's assigned to task D1. It can't also be assigned to task B2, okay? So one constraint is that these tile pieces in the puzzle must not be stacked if they're the same color. And also these tasks have order. A1 must be completed before A2. A1 is completed here. A2 starts here. So that constraint has been satisfied in this schedule. B1, B2, B3. Here's B1. Here's B2. Here's B3. Again, the order of those tasks are satisfied. So you can imagine that if you have many more tasks and many more machines, this puzzle very quickly becomes quite difficult to solve. So Basically, in today's terminology, we say this problem is NP hard. So if the manager comes in, let's say 30 minutes before the employees, that's the amount of time he has. And I'm saying he because these job shops, by and large, had male managers in the old days. That's how much time he has to find the optimal schedule or something that is close to optimal. Basically, at the end of the half hour, whatever schedule has been found must be executed. We can't afford to spend all day to find the optimal schedule. Okay, so maybe the manager comes up with these two and then decides that this one is a better one to use, and therefore goes ahead and uses it. Now, if this schedule is discovered, let's say after 20 minutes, and we still have 10 minutes of time, maybe we can play around. Like any optimization problems, sometimes local transformations may lead to a slightly better solution. So if you take this and then say, okay, I still have some time. Let's see what happens if I switch the order of these two. In other words, bring B2 over here, bring D1 here. Of course, if I bring D1 here, I must change the location of this one as well, which has been moved there. And, well, you see that we maintain the same 6 employees, 6 workers in this revised schedule, but 1 less time units. Instead of 16, it's now only 15. Okay, so this is typical of problems that we can solve optimally in a reasonable amount of time. We use heuristics to come up with reasonable schedules that are often not too far from the optimal. And then if we have time, we can sort of try to fine-tune the near optimal schedule to find something that is even closer to optimal by doing such local transformations and seeing what happens as a result of that. Another way to view this is that we try to minimize these white spaces, because those white spaces are basically wasted employee time and wasted machine time. Okay, so we try to pack these rectangles as close as possible to each other to reduce the amount of white space while honoring the constraints that I mentioned. Tasks, the same job should appear in the proper order. Blue boxes cannot be stacked on top of one another. Green boxes cannot. And orange boxes cannot be stacked. Okay, so this job shop scheduling problem has all the elements of the task scheduling problem that we have in today's computers. Basically, it's even more complex than the type of scheduling I will be discussing. See, not every machine can do the same job. Machines are specialized. So this task can be mapped only to this machine, this task only to this machine. Well, as I'm going to assume in the rest of this discussion that machines are uniform, and any task can be assigned to any machine. So this is sort of already more sophisticated than the type of scheduling that I'll be considering. Okay, so this is an overview of complexity of scheduling problems. Most scheduling problems, even with 2 processors, are NP hard, or many of them are NP complete. There are some exceptions. Easy or tractable or polynomial time cases of the scheduling problem include when we have unit time tasks and only 2 processors. So if you have unit time tasks with only 2 processors, then we have a polynomial time algorithm, but that's really not a very interesting case because you're simplifying the task and you only 2 processors. Most parallel processors have many more than 2 processors. Task graphs that are forests. Forests, if you remember from your data structure course are basically a collection of trees, okay, as the name implies. So task graphs basically that don't have cyclic connections. Okay, then with any number of processors, scheduling problem becomes tractable. Again, not many task graphs are forests, so it has limited usefulness. Now here are some surprisingly hard or intractable cases. Tasks of running time of 1 or 2 with only 2 processors. I'm assuming, of course, non-preemptive scheduling, which is what I said we will do. So as soon as you increase the complexity from unit time tasks to tasks that have running time of 1 or 2, two types of tasks. They're either unit time or they take up 2 units of time. Then even with 2 processors, the scheduling problem becomes NP hard. If you have unit time tasks, so you don't increase the complexity here, but then increase the number of processors to 3 or more. So with as few as 3 processors, the problem becomes NP hard, even with unit time tasks. So for this reason, many practical scheduling problems are solved by heuristics. And this is why we have so many papers published in the field of scheduling, because people come up with new heuristics, then they show that for some practical problems, those heuristics work well in the sense of coming up with solutions that are very close or reasonably close to optimal schedules, or with solutions that are better than what somebody else's heuristics came up with. So you either improve previous heuristics or you prove theoretically or experimentally that your solution, your heuristic solution, is very close to optimal. So scheduling literature is full of different heuristics and experimental studies of the performance in different domains. Okay, so that we have seen at least one type of scheduling algorithm, I'm going to describe a class of scheduling algorithms known as list scheduling. Okay, so far we have done just hand waving. You say, okay, you do this kind of mapping. How do you actually do that? Show me an example. Here's the example. So list scheduling basically works in the following way. We assign a priority level to each task. This is an artificial priority. Assume that tasks do not have an inherent priority. All tasks are created equal in our problems. But we assign an artificial priority index as an aid to execute our scheduling algorithm. So we assign a priority level to each task, and there are different ways of doing that. So basically, the different ways of assigning priority levels to tasks defines different instances of this list scheduling algorithm. Because once those priorities are assigned, everything else is automatic after that. There are no decisions involved. Construct a task list in priority order. Tag the tasks that are ready for execution. This will become clear through examples. At each step assigned to an available processor, the first tagged task. Then update the tags upon each task termination. So this is a possible priority assignment scheme. So I'm describing a class of algorithms, but only one instance of that class, which is associated with this priority assignment scheme. So instead of going through this word description, let me go directly to an example. So this is a task graph that we have seen before. It has a depth of 8. So 1, 2, 3, 4, 5, 6, 7, 8. That's the length of the critical path, T infinity. And that's basically the shortest time that we can take to execute this task graph. Okay, we set that as our goal. So find T infinity, the depth, and take T infinity as the goal for running time TP. If we can, we try to execute this task graph in 8 time units. If we can't, of course, then we have to accept 9, 10, or whatever number of steps that is required to complete it. But first, we aim for 8 time units. Now, if this task graph must be executed in 8 time units, the latest time that this node is executable is time unit 8. The latest time that these 3 nodes are executable is time unit 7, because if we are not done with these by time 7, then we can't execute this by time 8. So this is known as layering. We start layering the graph from the end. The end node is assigned the number 8. All prerequisites of the end node, direct prerequisites of the end node, 7. All the direct prerequisites of these nodes are layer 6, layer 5, layer 1. And then we take these numbers as priorities. So this will be priority task with priority 1, which is obvious, because if you don't start executing this one, then you can't do anything else in this task graph. This one has priority 2, this one has priority 3, this one has priority 4, this one has priority 5. Now, when you get to level 6, there are 4 tasks there, and we have to use a tie-breaking rule to assign priorities. So up to priority 5 was determined. So priority 6, 7, 8, and 9 must be assigned to these 4 tasks. We can do an arbitrary assignment, or we can use a secondary criterion for this. So for example, if a task has more descendants than other tasks, maybe we can give it a higher priority. The reasoning being that this is required for executing more tasks at the next level, therefore let's do this as quickly as we can. Now in this case, let's say each of these in level 6 is a prerequisite for only 1 task in the next level, so that rule doesn't help. So whatever tie-breaking rule, I assigned priority 6 here, 7 here, 8 here, 9 here. And then we go to this level. So 10, 11, and 12 must be assigned to these. Again, you have to have some tie-breaking rule. So that's part of the priority assignment scheme. Let's say I do 10, 11, and 12, and then finally 13. So I arrange the tasks in order of their priorities. Unfortunately, this example, I should have chosen a different example, because it's almost, the priority is almost the same as the task number, with one exception. Task 6 has priority 5, task 5 has priority 6. Okay, so I order the tasks in order of their priorities, and then put a star next to the only task that is ready to be executed. Okay, so the rest of the process, as I mentioned, is mechanical. This priority assignment is, you have to sort of do some work. The rest is mechanical. So let's say I have one processor. I take this task, which is the only one, and put it here, execute it on this one process. Then once task 1 has been executed, task 2 becomes ready, and that's the only one that becomes ready. So 2 is starred, and then once the processor becomes available, task 2 is executed, and so on. Okay, it takes 13 time units as expected because we have one processor. Here we have 2 processors. So 1, 2, 3 again. Then when we execute 3, Both for task 4, task 5, and task 8, just 1 minute. When we execute 3, 4, 5, and 8 become ready for execution. Okay, so 4 and 5, so 4, 5, and 8 will be starred in that case in the list. I take the first two, okay, in order of priority. 4 and 5, execute. 8 will be left. Then when 4 and 5 have been executed, okay, the 6 becomes, no, 4 and 5. When 4 and 5 are executed, yeah, 6 and 7 also become ready for execution. 6 has a higher priority, that's priority 5, so that one will be executed, and so on. So with 2 processors, we get a running time of 9. With 3 processors, this particular scheduling algorithm gets the optimal time 8. It doesn't guarantee optimal time, but it in fact does quite well for this one example. So with 3 processors, which is the minimum that we need to achieve the best running time, this scheduling algorithm actually achieves that best running time. And with 2 processors, it's easy to prove. In fact, you have done this as part of a homework problem, that you need at least 9 time units if you have only 2 processors. Okay, so this list scheduling algorithm is a reasonably good heuristic. It does well in most cases. Of course, you can construct for any heuristic, no matter in what domain it is, you can construct the worst case example. An adversary basically can construct the worst case example that defeats that heuristics. I mean, you can do that with any heuristics, including list schedule. Now, if your tasks are non-unit time, you can still use a version of this list scheduling algorithm. Here I've shown a very simple task graph that has unit time tasks, tasks that require 2 units of running time, and this one that requires 3 units. I've drawn the task like this to show that the layering works here as well. The critical path here is 2, 4, 6, 7. So this will be priority 7. There is nothing with priority 6 because no task starts here. This is priority level 5, layer 5, then layer 4, layer 3. Again, there's no layer 2, and layer 1. And then if there are multiple nodes on one level, so here this is priority 1, this is priority 3, there's just one task. Priority 4 has 2 tasks, okay? This one and this one. This is not part of that because this is basically the second half of that task. So priority 4, layer 4, takes these 2 tasks. Okay, so I assign priorities 1, 2. These 2 I use a tie-breaking rule. Let's say the longer task is given higher priority than the shorter task. 3, 4, 5, 6. So once I assign these priorities, again, I can schedule it on 1 processor, on 2 processor, on 3 processor using basically the same algorithm. Priority assignment is slightly different, but once priorities have been assigned, the rest of the scheduling algorithm does not change. Okay, eventually I'll add a section on fault-tolerant scheduling. Basically, if you're doing scheduling for some critical applications like space spacecraft guidance, and you want to make sure that if something fails midway through the computation, you can still honor deadlines and so on. You may want to do fault-tolerant scheduling, and this may involve using replicated tasks, schedule multiple copies of tasks so that if one of them does not run to completion, you still have a task that is completed. And there are a lot of interesting problems here. So for example, if the deadline is far away, maybe you don't start by scheduling multiple copies. You just schedule one copy and observe to see if it runs to completion without any problem. If it doesn't, then you may still have time to run replicas of the task later, only when failure occurs, which has low probability. So a lot of interesting problems exist in the domain of fault-tolerant scheduling. Okay, so Brent's scheduling theorem provides a very useful bound for scheduling, which is very comforting, because Brent's scheduling theorem says that the running time of a task with P processors, there is a naive scheduling algorithm. So even though scheduling is difficult, we have a naive scheduling algorithm that achieves this running time. What is this running time? Smaller than T infinity, which is the depth of the graph, plus T1 over P. Now, T infinity is the absolute minimum running time that you can have, and T1 over P is the maximum speed up that you can achieve with P processors. Okay, so what Brent's scheduling theorem, and I'll show the proof of it, tells us is that if T infinity is small, if you have a graph that has small depth, and therefore it is highly parallel, so that this T infinity is negligible compared to T1 over P, then you can basically achieve with that very naive scheduling algorithm near optimal speedup. So this is the optimal speedup, but because this number is added to it, it will be near optimal. Okay, P is the optimal speedup. T1 over P is the running time with the optimal speedup. And to that, you have to add T infinity. Okay, if a task graph is very long, okay, so that the depth is very large, then this basically says still the running time is not too much more than the depth of the graph. It's only more by this factor. Let's say you have a large number of processors, so that this term becomes small. Therefore, the running time is neither a lot larger than T infinity, nor a lot larger than T1 over P. This will become clear as we go. And here I sort of compare this to Amdahl's law, because if you can rewrite this inequality as S, which is the speed up, greater than, so basically speed up is T1 divided by Tp. So T1 divided by Tp, and Tp is replaced from that expression, is this. And this is reminiscent of Amdahl's law. It says speed up, ideally it is P, but it's not quite P. P is divided by 1 plus this. Okay? And what is this term? Hopefully this will be a small term, because if it's small, then the speed up will be close to P. Under what condition is this small? Okay, if T1 divided by T infinity is large, or T infinity divided by T1 is small. So T1 is the number of nodes in the graph, T infinity is the depth of the graph. So if that ratio, T1 divided by T infinity, is large, then this term can be small. Okay, so a highly sequential task will have a large depth. And this is the case for this example. Depth is 8, and T1 is only 13. So T1 divided by T infinity is not very large. Okay, it's less than 2, in fact. But the wider this graph, the more parallelism it has built in, then the better off you are in achieving a good speed up. Okay, here is proof of Brent's theorem. Brent says it's also based on a kind of layering, except you start from the top rather than from the bottom. Say, okay, the earliest time I can execute this node is 1, right at the beginning. The earliest time I can execute this node is 2, because I have to finish this one, and then the earliest time for this one is 3. The earliest time for these 3 is 4. So I basically assign to each node the earliest time unit that I can execute, assuming I have unlimited resources. So I have, let's say, 3 processors. I have 3 processors here to execute these 3 at the same time. Okay, assuming unlimited resources, I can execute this task graph in 8 time units. And this layering shows in each time unit which nodes I should execute in order to achieve that minimum time. And it also gives me basically a lower bound on the number of processors. I need to have at least 3, because some of these layers have 3 nodes. Okay, now Brent's scheduling theorem says, okay, let's execute the layers one at a time. So here I have 1 node in this layer, and if I have P processors, 1 divided by P, the ceiling of that is how many time units I will spend here. So basically 1 time unit. I need 1 time unit for this. I need 1 time unit for this. I need 3 divided by P time units for this. So N4 is equal to 3. There are 3 nodes. And if I have 3 processors, this will need 1 time unit. If I have 2 processors, this will need 2 time units. Okay? So this is a naive scheduling algorithm because I don't try to optimize. I just go layer by layer. Within each layer, I know that the tasks are independent of each other, so no problem can arise. Now, the difficulty of scheduling arises from the fact when I try to combine nodes in different layers. So for example, I say, okay, when I try to execute this, I better execute, let's say I have only 2 processors. If I execute 5 and 8 first with the 2 processors, and then this one in the next time units, then these 2 will be delayed. Okay, so I better execute 4 and 5 or 4 and 8 first, and then in the next time step, let's say I execute 4 and 5, I can execute 8 and maybe 6 at the same time. So nodes from different layers and the optimal schedule will be executed at the same time. This naive scheduling algorithm does not try to do that. It simply goes layer by layer, so it requires this much time. And the rest is very simple algebra. I basically remove the ceiling and add 1, because the ceiling of a fractional number, a non-integer number, is no more than 1 unit greater than it. So this is less than, because it's really not 1 unit, it's less than 1 unit greater. Okay, then the sum of 1 is t infinity, because I'm summing over this range. So that 1 gives me t infinity. And then t over p will be sum of nt divided by p. But sum of nt, sum of the number of nodes in different layers, is basically the total number of nodes. So that's t1. So that's the proof of Brent's scheduling theorem, that TP, this naive scheduling algorithm, the running time is no more than, is actually strictly less than, t infinity plus t1 over p. Okay, There are two corollaries of the scheduling theorem we just proved that are called good news corollaries. Remember, Amdahl's law was the bad news of parallel processing. Brent's scheduling theorem is the good news because of these two corollaries. One says if I choose the number of processors greater than or equal to T1 divided by T infinity, simple algebra here tells me that Tp, the running time, will be between T infinity and 2T infinity. Remember, this is the minimum, absolute minimum running time. It says if I have a sufficient number of processors equal to this ratio, at least equal to this ratio, then the running time will differ from this absolute optimal by no more than a factor of 2. Okay, which is a pretty impressive result for a naive scheduling algorithm. Corollary 2 says if I don't use too many processors, in other words, the number of processors is less than or equal to T1 divided by T infinity, again, simple algebra tells me that Tp will be greater than or equal to T1 over P and less than 2T1. Again, this is the absolute possible speed up that I can achieve. Okay, the fastest possible running time with P processors. And I can achieve something that is within a factor of 2 of that best conceivable running time with P process. Now, interestingly, these two conditions share in one point. That's basically when P is exactly equal to T1 over T infinity. Then both of these conditions are satisfied. So if you choose the number of processors approximately equal to T1 divided by T infinity, remember T1 is the size of the task graph, T infinity is the depth of the task graph. So you can say that T1 divided by T infinity is the average width of the task graph. So if you choose the number of processors equal to the average width of the task graph, you can have OP speed up because of this condition and near minimal running time because of this condition. Okay, so that's a very good news. It says, yeah, scheduling is difficult, but don't worry. Don't spend too much time trying to find the optimal scheduling algorithm, because even this naive scheduling algorithm brings you within a factor of 2 of these two important criteria for judging goodness of a scheduling algorithm. Okay, so this slide I showed you very early in the course. Amdahl's law is the bad news of parallel processing. Now we just learned that Brent's scheduling theorem is the good news. It says that optimal scheduling is very difficult, but even a naive scheduling algorithm can ensure a running time between T1 over P, and this one I've rewritten, again, it's simple algebra, T1 over P times 1 plus something. So the running time will be between T1 over P and T1 over P times something, a number that is larger than 1. But how large can this number be? This number, the larger T1 divided by T infinity, the smaller this number becomes. Okay, so if T1 divided by T infinity is very large, let's say larger than the number P of processors, then this will be 1 plus something that is smaller than 1, which is pretty good. And then the third part of the slide is not just one point that I can discuss. We have discussed ideas throughout the course that basically validate this cost effectiveness adage. The most cost-effective parallel solution may not be the one with highest peak operations per second because communications must also be considered. The greatest speed up, because the greatest speed up can come at a very high cost. Or best utilization. Just utilizing hardware doesn't mean much because you have to ask, what is the hardware busy doing? Okay, just being busy is not by itself a merit. So let me just briefly discuss some of these ideas. So why peak operations per second isn't a good measure? Because we have data from supercomputers, for example, that have 100 petaflops peak performance, but for certain applications, they may exhibit 10 petaflops, what we call sustained performance. In other words, as they run some class of application, their processing capability is 10 petaflops, not 100 petaflops. Another supercomputer that has perhaps 50 petaflops peak performance. So in terms of peak performance is lower rated than this one, but may exhibit something greater than 10 petaflops sustained performance. Okay, so the peak petaflops is not really a good measure for comparing. Okay, the utilization analogy here, I've shown an example. Suppose you're comparing buses versus private autos. Let's say a bus has 50 seats, and on average, let's say there are 10 riders on the bus. So the utilization of the bus is only 20%. 20% of the seats are occupied on average. Okay, let's say an auto has 5 seats. On average, there are 2 riders in it, so the utilization is 40%, 2 divided by 5. Can we say that autos are more efficient than buses? No. In terms of fuel efficiency, environmental considerations, and so on, buses may still be more efficient, even though they have a smaller utilization factor according to this measure. Okay? And the final thing, greatest speed up, this is basically these charts is from Amdahl's law, but similar charts are observed throughout the parallel processing field, where as you increase the number of processors, speed up increases rather quickly at first, linearly, but then it flattens. In the case of Amdahl law, it flattens because of that sequential fraction. In other cases, it may flatten because communication overhead takes over. In fact, not only it flattens, it may actually start dropping off at some point when the overhead becomes intolerable. Okay? Now, let's take Amdahl's law. So the speed up actually goes up, but the rate of it going up slows down. So let's take this red curve. Say, okay, if you're interested in high performance and the best speed up in this range, you have to use 100 processors at this point, because the speed up there is a little bit more than here. However, you must ask yourself as an engineer, do I really want to pay the additional cost of going from, let's say, 32 processors or whatever the number is here to 100 processor just to buy this much improved performance? The answer may be no. So this may be really the most cost-effective design when you take everything into account. So 100 processors cost more in terms of the processors you use, cost more energy because 100 processors are used. This one uses less energy, uses fewer processors and therefore lower cost, and so on. And in fact, because you have fewer processors, communication overhead may also be reduced. So when the curve flattens like this, usually the most cost-effective solution is not at the very top, but when the increase is rather quick here, it pays us to go to higher number of processor. But at some point, it may even come before here. You ask the question, is it worth spending this much more money to go from this performance to this performance? And the answer is, of course, application dependent. But as an engineer, you have to ask that question. Okay, load balancing I'm going to skip. So let me go to chapter 18 and discuss some of the ideas here, very few of the ideas. So basically, caching, cache coherence, we already discussed before. So I'm going to skip a lot of these ideas and start with a brief discussion of disk memory. So this is a typical disk memory used in modern computers. There are multiple platters to increase the capacity. Each platter has 2 recording surfaces, the top and the bottom of it. And you have 4 platters, you have 8 recording surfaces. So this is a way of increasing the capacity. In many laptops, you have just 1 platter so that you get the thinner disk. But if you really want high capacity, then using multiple platters is the way to go. The heads are mounted on this head assembly and that can rotate using this actuator. So the rotation of this actuator moves the head across the disk, aligning it with different tracks. Okay, so basically when you access this disk, whether it has a single platter or multiple platters, so the multiple platters will have their own, each platter, in fact, each platter surface has its own read-write head. So this particular arm will have 2 read-write heads, one facing upward to read the bottom of this platter and one facing downward to read the top of the. So having multiple platters has no speed implications for reading and writing. So there are 3 components to the disk access time. The seek time is how much time it takes for the head to move from its current location, perhaps from its rest position outside the disk, to the track or the cylinder that needs to be accessed. Then once it is aligned, the head is aligned with the cylinder or track, it has to wait until the disk has rotated and the data of interest is under the head, and then it has to wait this much time to read all the data in a sector. Now this third component is usually small compared to the other 2, so we can safely ignore it. But the other 2, each one is on the order of several milliseconds. Okay, so a millisecond is an eternity compared with electronic speed. So millisecond compared to nanosecond or fraction of nanosecond for gate speed. So this disk access time is a major bottleneck in achieving very high performance. So this is the formula often used in terms of how many cylinders you have to move. And basically there's a constant that basically the inertia of the head before it starts moving. And then the linear, so the head basically accelerates, then goes at constant speed for a while, and then decelerates. So this is basically the constant speed part, and this is the acceleration and deceleration part. So that's a model that is used for how much time it needs. And so the seek time can be 0 if you happen to be reading. So once you read from this cylinder and then you want to read something else from the same cylinder, then the seek time will be 0. But it can be as high as tens of milliseconds if you want to go from one end of the disk to the other end. Similarly, rotational latency on average is half a disk rotation. So that's also several milliseconds. In fact, this formula says 30,000 depending on revolutions per minute. So if you have the disk that rotates at 10,000 RPM, the average rotational latency is 3 milliseconds. That's the time for half a rotation. If it rotates at 7,500 RPM, then the average will be 4 milliseconds. So it ranges from 0 to 8, the average being 4. So early in the, I'm going to skip this one. The chart says that disk seek time or its rotational latency and DRAM access time have not improved as quickly as CPU cycle time. So both we have the memory wall because DRAMs are now much slower than CPUs, and disks are also much slower, relatively speaking. So here, let's say the ratio of the disk access time to, let's say, CPU cycle time was 5 orders of magnitude, 10 to the 5. Okay, here now it is 1, 2, 3, 4, 5, 6, 7. 7 and some change orders of magnitude. Okay, so it's very important now to improve the performance of disk memories. Okay, so early in the history of high performance computing, people tried all sorts of neat tricks to achieve this improved performance. And this diagram shows 2 of those examples. One was the head per track disk. Instead of having one head that is shared between the tracks and it has to move back and forth, creating that seek time, we have one head per track, and therefore no mechanical movement is needed. You just select electronically the head that needs to read. So you basically eliminate seek time. And then if you include 2 sets of heads, you can also cut down the rotational latency by half. So that now instead of half a disk rotation on average, you have a quarter of disk rotation on average. Well, pretty neat idea, except that this didn't work out in practice. Why? Because, developing a new disk with its associated technology is very costly. It takes millions and millions of dollars to design a new disk and all those heads and other associated electronics. And the market for high-performance computers was very limited in those days. It's still limited compared to the PC market. You sell many millions of PCs. In the case of very high-performance computers, the sales figures are in the hundreds or at best in the thousands. Okay. So it doesn't pay to spend a lot of R&D time developing special disks for these high-performance computers. So the idea occurred in the 1980s, and then especially in the 1990s, people worked on this. Why not use the same disks that we use for PCs for high-performance computers? Well, there are 2 problems. Those disks are not large enough in terms of capacity. We need, petabytes of data. And the best disks we have these days are terabyte disks, multiple terabyte disks. So capacity, we need higher capacity. They are not reliable enough. They're reliable for a PC, for a laptop, because you just have one disk, and if the mean time to failure of your disk is, say, specified as 20 years, well, in the time that you own your laptop, it's very unlikely that your disk fails. Imagine a data center that has tens of thousands of disks, then it's very likely that 1 or 2 of those disks will fail over a short period of time, and therefore data loss occurs. So they're not reliable enough for high capacity applications. So this led to the idea of RAID, redundant arrays of independent disks. I used to stand for inexpensive, but nowadays, every disk that is on the market is actually inexpensive. There's no such thing as an expensive disk. So RAID now stands RAID for redundant arrays of independent disks that solve both of these problems. So there are products on the market that put many disks. There are small products that may have 4 or 8 disks in them. There are larger products that may have hundreds, and then you can put multiple of these cabinets in the data center and expand it indefinitely. So the idea is that these multiple disks from external or interfacing point of view behave as a single disk. So you basically write to the controller of this RAID as if you're writing to a single huge disk. Internally, the disks are organized both to achieve high bandwidth, so you can read from multiple disks at the same time to achieve high bandwidth, and also high reliability. Data is encoded in such a way that if a single disk fails, and in the modern version RAID 6, even if 2 disks fail, you don't have any data loss, okay? So the rest of the discussion in this chapter is these various RAID levels that I'm gonna skip because some of these only have, historical significance. RAID level 3 basically does the following. It takes pieces of data. Let's say I have a particular file with pieces A0, A1, A2, and A3. I compose a parity block from those blocks. Okay? And then, so basically RAID 4 is probably better because in RAID 3, those are not blocks. Those are smaller pieces. So here's a block of data. These 4 blocks together constitute a file. So because they're on 4 different disks, I can read them simultaneously, therefore achieve high bandwidth. And then I compute a parity block, which is basically the XOR of all of those blocks, and store it here. Now, if I lose this disk crashes, or this particular data block becomes unavailable, I can reconstruct it because A0 XOR A1 XOR A2 XOR A3 is equal to A parity. A2 can be reconstructed as A0 XOR A1 XOR A3 XOR A parity. Of course, this takes a long time because if this entire disk has crashed and failed, I have to read the contents of all of this disk, all of this disk, all of this, and all of the parity disks in order to reconstruct the contents of this disk. And there's a spare disk on the side here that I can use to replace this failed disk. So that's how reliability is achieved. Except that as I'm reconstructing this disk, which may take many hours, given how much data is involved, it's not unlikely that the second disk failure occurs, this crash occurs, and therefore I lose data. So the hope is that that second crash does not occur within those few hours that I'm reconstructing. But this scheme also has another problem. If within this file I change some data, some word in this part of the file, then the parity of the file changes, okay? So anytime I write something to one of these disks, I have to write the corresponding parity block here. So this parity disk can become a bottleneck because anytime I write anything in these 4 disks, I have to write something, okay? So RAID 5 solves this problem by distributing the parity blocks rather than having a dedicated parity disk. Parity blocks are viewed just like data blocks. So A0, B0, C0, D0 have their parity here. A1, B1, C1, E1 have their parity on a different disk. Doesn't matter, okay? So that's just a minor improvement that removes that parity disk becoming a bottleneck because parity writes are also distributed to different disks. And then RAID level 6 adds a second error detecting, error correcting. So we have the parity as before that allows us to tolerate one disk failure. There's a second error correction mechanism. Usually it's Reed-Solomon, but it doesn't have to be Reed-Solomon. So this code is used. So basically A0 and B0 have the parity block B0, and also this other secondary error correcting code information. And therefore, if this disk fails and I'm trying to reconstruct its contents and suddenly another disk also fails, I don't lose any data because the secondary error correction mechanism protects me against loss of data. Okay, so I'm going to skip all these. If you are interested in more detail here, you can read on your own. Also, in my course on dependable or fault-tolerant computing, I discuss RAID in more detail. So, okay, I'm going to skip section 18.6 because some of this, again, was discussed in our discussion of shared memory. And therefore, this brings us to the end of the course, Parallel Processing, ECE 254B. I hope you enjoyed the course and learned useful information from it. At the very least, this course, the area of parallel processing is very broad. There are multiple journals for publishing papers in it, multiple conferences annually to discuss new ideas. So what I provide in this course is a framework for you to understand the basic concepts of parallel processing and know the terminology and main ideas so that you can basically branch out and read about different aspects of parallel processing according to your interest or whatever whenever need arises in the job that you're doing after you graduate. Okay, so please take care, and I hope to see some of you in my other graduate courses in future, including my ECE 252B computer arithmetic course, which is coming up in spring order. Okay, bye-bye for now. Take care.